Welcome to The Explainer. Today, we're going to dive into this incredible story of resilience, how life can spring back from what seems like total devastation. We're going to uncover the hidden rules that govern, well, every living thing on the planet.
So let's set the scene. It's 1980. Mount St. Helens in Washington erupts with just unbelievable force. It buries the entire landscape in this thick blanket of superheated rock and ash. What was left was, for all intents and purposes, a sterile, dead world. For 2 whole years, this place, which they started calling Pumice Plain, was basically a ghost land. And then, scientists found something, a single sign of life, one prairie lupine. And what's wild is that this one little plant kicked off a complete ecological recovery. So how on earth is that even possible? To figure that out, we're going to trace this amazing story of rebirth, step by step. And as we do, you'll see the universal rules of life that this little plant put into motion. You know, from that single lupine in '82, a whole chain reaction started. First came the insects, then other plants started to pop up, then small animals, and believe it or not, within just 2 decades, predators like weasels were back. Pumice Plain was a living, breathing ecosystem again. But this wasn't magic. It was all following a very specific set of biological rules. All right, let's get into it. To really understand the incredible power of that one little plant, we need to get a handle on the 3 essential jobs, the 3 roles that every living thing plays in an ecosystem. First up, we've got the producers. These guys are the absolute foundation of everything. Just like our heroic lupine, they take stuff that isn't alive, like sunlight, water, and air, and they make their own food. They literally create life from scratch. Next, you've got the consumers. And yep, this is pretty much every animal you can think of, including us. Consumers can't make their own food, so they have to get their energy by eating other living things, whether it's plants or other animals. And last but definitely not least are the decomposers. Think about things like fungi and bacteria. These guys are nature's ultimate recycling crew. They break down all the dead stuff and waste, returning nutrients to the soil so the producers can use them all over again. Okay, so this brings us to a really critical idea. See, energy flows through an ecosystem. It's like a one-way street. It comes in from the sun, it gets used, and then it's lost as heat. But matter, all the physical atoms, that's totally different. It's on a continuous loop, getting recycled over and over and over again. Okay, so we have our players, the producers, the consumers, and the decomposers. Now let's see how they actually connect and start moving all that energy and matter around in a place like Pumice Plain. It all starts with something you probably remember from science class, a food chain. It's just a simple, straight line showing who eats whom. So, the lupine gets energy from the sun, an insect eats the lupine, a mouse eats that insect, and then a weasel eats the mouse. Easy, right? But, you know, life isn't that neat and tidy, right? In the real world, animals eat lots of different things. So you have all these different food chains crossing over and connecting with each other. And that creates something much more complex and, frankly, more stable, a food web. I mean, just look at this rainforest food web. You can see right away how tangled it gets. A jaguar doesn't just eat monkeys, it might also eat tapirs. And the monkey isn't just eating one thing either. It's this complexity, this interconnectedness, that actually gives a whole ecosystem its strength. So here's a huge question. When that weasel eats the mouse, does it get all the energy that the mouse got from the insect and that the insect got from the plant? The answer to this actually explains the entire structure of, well, every ecosystem on Earth.
No way. Not even close. See, most of the energy any living thing consumes gets used up immediately, just for its own life processes. You know, moving around, breathing, just staying warm. A bunch is also lost as heat. Only a teeny tiny fraction actually gets stored in its body, ready for whatever eats it next.
And this is what leads us to a really cool concept called the energy pyramid. It's basically a picture that shows how the amount of usable energy just plummets as you go up each step of the food web. A pretty good rule of thumb here is the 10% rule. On average, only about 10% of the energy from one level actually makes it to the next level up. This is exactly why there's always way more grass than there are gazelles and way more gazelles than there are lions. There just isn't enough energy at the top to support huge numbers of predators. So, this upward flow of energy literally defines the shape of life. But what happens when something harmful gets into that food web? Well, it turns out those exact same pathways that move life-giving energy from the bottom to the top can also become highways for some really dangerous stuff.
And this is where we have to talk about two really important and kind of scary ideas. First, you've got bioaccumulation. That's just a toxin building up inside one single animal over its lifetime. But then, there's biomagnification. This is when that toxin gets more and more concentrated as it moves up the food chain. And this is where things get really serious.
Let me walk you through it. Say a little fish absorbs 1 unit of some toxin. Not a big deal for that one fish. But then a sea lion comes along and eats, 10 of those fish. Well, now it has 10 units of that toxin inside it. Then an orca eats 10 of those sea lions, and boom, it's now carrying 100 units. A dose that was harmless at the bottom of the food chain can become lethal at the top.
And that brings us right back to the beginning. The exact same rules of energy flow that allow life to make a miraculous comeback on Mount St. Helens are also what make the animals at the very top so incredibly vulnerable to our pollution. The very rules that can rebuild a world can also endanger it. Which leaves us with a pretty big question, doesn't it? How do we balance that difference?